Hello, my dear students. Welcome back to the online lecture video series on electromagnetic theory by alias Deepak. In the previous lectures, we have seen the modified Maxwell's equation for magnetic fields, and then we have updated the Poisson's equations for time varying electric and magnetic fields. In the current lecture, we would be discussing the Maxwell's equations for time harmonic fields, and the Maxwell's equations would be in phasor form. So the contents in today's lecture are: we would discuss what are the various types of vector fields, and then we would discuss how to represent a time harmonic field using its phasor, and then we would explore the relationship between phasor of a time harmonic field and the field obtained by differentiating the given field with time. And then we would do the same for integration. And then we would express the Maxwell's equation for time harmonic fields in phasor form. So let us start our discussion by discussing various types of vector fields and how they look. We know that vectors are physical quantities which have direction and magnitude. And if they are simple vectors, those direction and magnitude are fixed and they do not vary by any factor. So if we have a vector, v bar would be looking like this in Cartesian coordinate system, where a, b and c are constants. They are not changing with time. Similarly, we have discussed static vector fields. The meaning of static is time static. That is, they do vary with space because they are fields. They do vary with space, but they do not vary with time. We have seen that any static field could be written as directed sum of three scalar fields, where the directions are along ax cap, ay cap and az cap. And these three scalar fields are independent of each other. Similarly, we have started our discussion on time varying vector fields. That is, these vector fields vary with both space and time. The form they take are of this. Here, you may identify the difference between S bar and T bar. The AX in S bar is dependent only on X, Y and Z, whereas AX in T bar is the function of X, Y, Z and time t. So this is the difference between a time varying vector field and static vector field. That is, they do change with time, whereas static vector fields don't change with time. Now, time harmonic vector fields are a special case of time varying vector fields where they do vary with space and time, but the variations in time are periodic. That is, for example, at a point, value of any vector field is 10ax cap, and at first point and the second point it is 10ay cap, and at third point 10az cap at time t1. And after t2, there may be some 5ax cap, 5ay cap, and 5az cap. But after some time, T1 plus capital T, the vector field at point A1 would be equals to 10ax cap, and point 2 would be equals to 10ay cap, and point 3 would be equals to 10az cap. Not just that, after time T2 plus capital T, at point 1 it would be 5ax cap, at point 2 it would be 5ay cap, and at point 3 it would be again az cap. So this is how the time variations occur. That is, after every t seconds. That is not just t1 plus t, even at t1 plus 2t, the values would be like this. For every t1 plus nt, the values would be the same. And every t2 plus nt, the values would be of this sort. So these type of variations are called as time harmonic variations. And they would be looking like this, where this AXP, AYP and AZP are periodic variations in time. Let us look at some examples of time harmonic fields to get a clear idea. The first example I am considering is TH1 bar is equals to 5 cos 10 to the power of 6t minus 10x in the direction of AZ cap. So it is very clear that after every 2 pi by 10 to the power of 6 seconds, this would repeat. Similarly, we have a second vector field which is varying after every 2 pi by omega seconds. We are talking about variations with respect to time. And you may have a vector field which is looking like this. See this. This is looking like a static vector field S bar, and it is being multiplied by a rectangular pulse train. This is the time variation. This is giving the time variation, and this is giving the space variation. So this is varying with both space and time, and because this is a rectangular pulse train, and how will a rectangular pulse train look? The rectangular pulse train look like this. So it is going to repeat after every t seconds. But in these t seconds, it is kept constant for kt seconds, and it is turned off for t minus kt seconds. And this k is called duty cycle. So this is an example on how a time harmonic field can look. Note that this rectangular pulse train need not be the only periodic signal. It can also be any periodic signal p of t. So any static field which when multiplied by a periodic signal p of t would give you a time harmonic field. Any static field when multiplied by a periodic signal would give us a time harmonic field. So now to analyze any time harmonic field, we should be analyzing this periodic signal and this static field. We have already seen some analysis of this static field. Let me discuss how we can simplify the analysis for every periodic signal. To understand how we can simplify the analysis of a periodic signal, let us discuss the concepts of Fourier series. Fourier series representation of a signal says that any continuous periodic signal can be expressed as sum of sine, cosine and dc. That is, if you have a periodic signal p of t, this can be written as a naught plus sigma n equals to 1 to infinity a n cos 2 pi n f naught t plus sigma n equals to 1 to infinity b n sin 2 pi n f naught t. Here, this a naught is the average value of P naught, also called as DC. And this F naught is the fundamental frequency. The relationship between fundamental frequency and time period is that F naught equals to 1 by capital T. F naught is the fundamental frequency and F naught is the nth harmonic of the fundamental frequency F naught. And An is the contribution of this cos 2 pi nf naught t towards this p of t, and Bn is the contribution of sin 2 pi nf naught t in p of t. That is, any periodic signal can be expressed as weighted sum of sine, cosine, and of course there is a DC value. Now, how will this ease our mathematical analysis? How will this simplify the analysis? So, if we are to analyze the response of any system, the system being a linearly time invariant system, for a periodic signal p of t, then we need not be analyzing for all the frequencies it has. Instead, we use the principles of superposition and scaling to simplify our analysis. How to do that? The scaling principle says that analysis of sinusoidal signal for one frequency can be extended for all the harmonics. That is, if you analyze the signal for one frequency f naught, then you can apply the same analysis for any harmonic and f naught using the properties of scaling. And using the properties of superposition, the weighted sum where weights being An and Bn will give us the final results. So, in order to simplify the mathematical analysis, we can consider only sinusoidal signal and do the analysis as their results can be extended for all the periodic signals. So from now on, that P of t, whatever we have discussed, that P of t is just cos omega t or cos 2 pi ft. Whatever we analyze for this can be extended for any periodic signal which we would get. That is why in many cases, not in just electromagnetic theory, wherever you go, people generally consider only a sinusoidal signal for the analysis, and then they can extend this analysis for any given periodic signal. Let's see the phasor representation and how any field can be represented as its phasor. Let us have a vector field A bar which is equals to AS bar times cos omega t plus theta, where theta is the phase of the sinusoidal signal. That is, the value of the field at time t equals to 0. Now, this can be written as real part of as times exponential of j omega t plus theta, because exponential of j omega t plus theta is cos omega t plus theta plus j sin omega t plus theta. If I consider the real part of it, the real part is only cos omega t plus theta. Now, using the principles of exponent multiplication, e to the power of x plus y can be written as e to the power of x times e to the power of y I can rewrite this expression to be real part of exponential of j theta times exponential of j omega t. This can be clubbed together to give us the phasor of a bar. So phasor of any vector field b bar is such function such that when I multiply Bp with exponential of j omega t, then the real part of this should make you back the B bar. Then this Bp bar is the phasor of B bar, where omega is the frequency. In fact, the angular frequency. AP bar is called as the phasor of A bar. And this is the phasor representation of time harmonic fields. Now, what happens when you differentiate a field, time harmonic field in time? So, if I differentiate A bar in time, then I am differentiating the real part of AP bar exponential of j omega t. The differentiation and the real operation, both being linear, can be rearranged. This is the real part of differentiation of AP bar exponential of j omega t. Now, applying the principle of UB, I get that AP bar times dou by dou t of exponential of j omega t plus exponential of j omega t times dou by dou t of AP bar. We have already seen that AP bar is not a function of time. Therefore, its differentiation would result in 0, whereas the differentiation of exponential of j omega t would result in j omega exponential of j omega t. You may see dou a bar by dou t, which itself is also a time harmonic field, is the real part of AP bar j omega times exponential of j omega t. Now this is the new phasor of dou a bar by dou t. So the phasor of dou a bar by dou t is AP bar j omega, where AP bar is the phasor of A bar. So if somebody tells you that 3ax bar is phasor of some vector field B bar and asks you what is the phasor of dou B bar by dou t, then the answer is 3j omega ax cap. So this is the relationship between phasor of a time harmonic field and phasor of time differentiated time harmonic field. Similarly, if I consider the integral of a bar dot d bar dt is equals to integral of real part of AP bar exponential of j omega t. Again, the real part and the integral signs can be exchanged. This is the real part of integral of AP bar exponential of j omega t. We have already seen that AP bar is independent of time. So therefore, it is AP bar times exponential of j omega t. Exponential of j omega t gives me 1 by j omega exponential of j omega t. Therefore, the phasor of integral of a bar dot dt is AP bar by j omega. AP bar by j omega is the phasor of integral of a bar dot dt, where AP bar is the phasor of a bar. So if somebody gives you same example for a vector field B bar, if the phasor is 3ax cap, what is the phasor of time integral of B bar dot dt? Then the answer is it is 3 by j omega x. where omega is the frequency of V bar. Now let us establish the Maxwell's equation in phasor form. We know that divergence of electric flux density is equal to rho V. So, the divergence of phasor of electric flux density would be the phasor of rho V. Similarly, here we have that the curl of electric flux density is minus dou V bar by dou T. So if I write this in phasor form, curl of EP bar would be equal to the phasor of minus dou V bar by dou T. If phasor of V bar is VP bar, then from the principle which we have obtained earlier, then the phasor of dou P bar by dou T would be VP bar J omega. And for minus dou P bar by dou T, it would be minus VP bar J omega. Therefore, del cross EP bar would give us minus J omega VP bar. These are all the phasors. We are expressing the Maxwell's equation for phasors. Similarly, I have del dot B bar is equals to 0. Now, if I write it in phasor form, then del dot BB bar is equals to 0. Similarly, del cross H bar is equals to J bar plus dou D bar by dou T. Now, if I write it in phasor form, I would get that the phasor of this is JP bar, but the phasor of this as similar to that of this is J omega PP bar. Therefore, del cross HP bar would give me JP bar plus J omega PP bar. That's it for today's module. And these are differences. This is where I have downloaded the rectangular constraint image, and for a regular discussion, you may follow Matthew Sadiku, and for any queries, please ask in the comment section. Thank you.